Magnetic properties. Electron in an atom behaves like a magnet. Its magnetic moment is due to 1. Orbital motion around the nucleus. 2. Spin around its own axis. Magnetic moment is calculated by the formula mu equals to square root of n plus 2 Bm. N is number of unpaired electrons. Magnetic moment is assured in terms of Bohr magnetism Bm. 1 Bm equals to Eh by 4 pi mc equals to 9.27 into 10 power minus 24 ampere meter square. E. Charge of electron. H. Planck's constant. M. Mass of electron. C. Velocity of light. Mu equals to square root of n plus 2. N mu Bm. 1 1.7, 2 2.8, 3 3.8, 4 4.9, 5 5.9. Based on magnetic properties, there are 5 types of substances. A. Diamagnetic. B. Paramagnetic. C. Ferromagnetic. D. Antiferromagnetic. E. Ferromagnetic. Diamagnetism. Diamagnetic substances are weakly repelled by the magnetic field. These substances do not contain an unpaired electrons. All the electrons are paired, which cancel their magnetic moment. Example, H2O, NaCl, etc. Paramagnetism. Paramagnetic substances are weakly attracted by the magnetic field. These substances contain one or more unpaired electrons, which is the cause for their magnetic moment. These lose their magnetism in the absence of magnetic field. Example, O2, Cu plus 2, Fe plus 3, etc. Ferromagnetism. Ferromagnetic substances are strongly attracted by the magnetic field. These substances can be permanently magnetized. In these substances, the spin of all the unpaired electrons will be parallel. Example, Fe, Co, Ni, CrO2, etc. Antiferromagnetism. Substances existing antiferromagnetism also contain unpaired electrons. By the alignment of these electrons, magnetic moment of atoms or molecules cancels each other. As a result, the net magnetic moment will be zero. Example, MnO, V2O3, NiO, etc. Ferromagnetism. Substances existing ferromagnetism also contain unpaired electrons, but the alignment of these electrons are unequal, resulting a less magnetic moment. On heating, these substances converts to paramagnetic substances. Example, Fe3O4, Mg Fe2O4, Zn Fe2O4, Cu Fe2O4. V2O3 converts to paramagnetic at 150 Kelvin and NiO at 523 Kelvin.
So remember one thing, see, the magnetic property of any chemical substance is basically depend upon two things. One, the electron which is rotating on its own axis, and another feature, the electron is revolving around the nucleus. Getting my point? Basically, the magnetic property of any chemical substance result first of all from the fact that moving electron act as micromagnet. Okay, and electron is having a two sort of spin. One is a orbital motion, another is a spin motion. So what is orbital motion? If electron is moving around the nucleus, then that will be considered as orbital motions. And if electron is moving its own axis, then it is called as spin motions. So these two contribute to the magnetic behavior of any species. Okay. So if you will remember, in case of transition element, if someone will ask, how do you calculate the magnetic moment? Your formula is mu is equal to root of N plus 2, right? But in this case, especially in case of lanthanide and actinide, basically the magnetic property is defined with S as well as L. Just now I told you spin motion as well as orbital motion. So here the formula is mu is equal to root of 4ss plus 1 plus LL plus 1. Right? Why is it happen? See, whenever any substance in the magnetic field, there will be a field to induce the motion of electron in its material in such a way that it will generate a magnetic moment. Right? Now see, there will be two probability. Either the resulting material will repel the applied magnetic field or it will align. If it will be repel, then it will be called as diamagnetic, and if it will align with the magnetic moment, then it will be called as paramagnetic. Right? Okay. Now here, if you will see, most of the element under Lanthanide series used to have paramagnetic nature. Why? Because they do show the unpaired electron available in their orbital. But there are the elements which are having a paired shape of configuration. Those will be comes under the diamagnet. Okay. Now, this is the formula from which you can calculate their magnetic moment. Always remember, in this case, the spin orbit coupling is higher than ligand field. Right? If someone will ask why we do calculate the magnetic moment in case of transition element with the formula of root N plus 2 in case of transition element, whereas in case of F block we do apply this formula. So the answer is, in case of lanthanide, spin LS coupling जिसे बोलते हैं, LS coupling is far greater than crystal field coupling. Okay, I will also discuss about why it is so. Right? Let us come one by one. First of all, this is a formula which we are going to implement to calculate the magnetic property of any element belongs to 4f and 5f series. Okay. Another feature which you always remember, if any element is having unpaired electron, they will come under paramagnetic nature, and if there will be a pairing of electrons, then they will become under the diamagnetic behavior. Now come to the point that why this lanthanide used to give different formula and why we are applying different formula for in case of lanthanide. Just now I told, because remember, in case of lanthanide, the spin orbit coupling is having more value, is having a great value with respect to the crystal field stability. That's why we don't consider the environmental effect over here. Now, as a layman language, I must say that in case of D block element, the orbital contribution is usually quenched by the interaction with the electric field of ligand in its environment, and that's why the magnetic moment can only be calculated by the spin contribution. Right? However, in case of lanthanide, the 4f orbitals are well shielded from the surrounding by the overlying of 5s and 5p electrons. So it is not possible by ligand to to directly correlate with the 4f orbital. That's why the crystal field effect is negligible in case of lanthanide, and we prefer the formula for root of 4 ss plus 1 plus ll plus 1. Now see here, 4 ss, s belongs to spin momentum contribution and l belongs to orbital momentum contribution, right? So far we have discussed, like, if we are trying to calculate the magnetic moment in case of transition element, the formula will be root of 4 ss plus 1. But if you are trying to calculate the magnetic moment for lanthanoid, the formula which is mentioned in the screen, right? I told you what is the difference and why this type of anomalous behavior used to be monitored in case of lanthanoid. Let us move ahead now. Next is, you will sorry, beta.
Can you explain it, sir? Once again.
Okay. So see, if you will remember, in case of transition element, you used to calculate the magnetic moment by the formula of root nn plus 2, or you can say root of 4 ss plus 1. But just now I told you, in case of lanthanide, the magnetic moment can be calculated by the formula of 4 ss plus 1 plus ll plus 1. In short, the basic difference between both the formulae is, in case of lanthanoid, orbital and spin contribution used to be considered, whereas only spin contribution is considered in case of transition element. Now the question is why? See, in case of lanthanide, remember that the orbital contribution is quenched. Why? Due to the interaction with the electric field of ligand in its environment. That's why only spin contribution comes into the picture in case of transition element. Whereas in case of lanthanol, since the 4f orbitals are well shielded from the surrounding by overlying 5s and type B electron, it is not possible to explain their magnetic movement in terms of number of unpaired electrons alone. I must say that the environmental effect does not participate significantly in case of lanthanoid. Why? Because 4f orbital is quite shielded in nature as respect to 3D in case of transition. Okay. I mentioned also that 3D transition is quenched by the interaction of magnetic field of ligand. Right? And if you will solve this formula, you will come to know that root nn plus 2 is going to be applied in case of transition element. Okay. So this is the reason which we have discussed just now. Let us move ahead. Now you see, this is a table where I have mentioned that what is the calculated magnetic moment has noticed in case of lanthanide and what observed value has been found. Now see, 4f0 lanthanum plus 3, since no electron is available in case of f orbital, so expectedly the magnetic moment will be 0. And we are able to get it, the 0, in observed as well as calculated. Once we move from lanthanum to cerium, prosmedium, neodymium, promethium, and so on, you will notice that the most of the magnetic moment do show a quite similarity with the observed value. Right? For example, cerium, you will see calculated is 2.54, and experimental value is 2.3 to 2.5. So you can say that it's nearby. But there are the species which shows the deviations from the calculated value as well. For example, European plus 3. See here, calculated corresponds that the value will be 0, whereas in case of observed, they are able to get it 3.4 to 3.6. Okay. Now, any other significant difference you are able to notice, then let me know. One more is samarium plus 3. Now see, only two significant difference usually been observed in case of calculated and observed magnetic moment value, and those are samarium plus 3 and europium plus 3. The calculated value corresponds that in case of samarium, the magnetic moment is 0.84. In case of europium, the magnetic moment is 0. Now you compare with the observed. Observed means experimental value. It is 1.5 to 1.6 in case of samarium, whereas in case of europium, it is 3.4 to 3.6. What calculated value corresponds that? It should be 0. Right? So it was quite surprising. One calculated observations corresponding the value is 0, whereas observed is belonging to 3.4 to 3.6. Right? Now, if you will notice in case of gadolinium, it is 7.94 and observed is 7.80. Right? Why I have mentioned this red box over here? Because this is the only element where the magnetic moment is calculated only by the spin of electron. No orbital contribution is applied. Okay, so it is an important point. Among all 14 elements, gadolinium plus 3 is the only element where orbital contribution does not take a part. Only spin. Now the question is why? I shall ask to you, and even later on I will explain you why it is. Right? For a while, just remember that gadolinium is the only element where the spin contribution takes part rather than orbital. The remaining rest of the 13 element, orbital as well as spin contributions takes part. Right? Most of the elements do show the similar magnetic moment in between of calculated and observed value. Only two elements, samarium plus 3 and europium plus 3, have shown a significant difference from the observed magnetic moment. Now, why it is? Why it is the case that in case of samarium and europium plus 3, they do show the difference from the calculated value? It means something important is going to be happening, right? Now see, in case of samarium plus 3 and europium plus 3, the spin orbital coupling is only about 300 to 400 centimeter inverse. Right? Now, this means that the energy in the ground state and next higher state is quite small. Now, what would happen? This energy can easily be achieved by the thermal motions, and which promotes the electrons to ground state to first excited state. And due to this, it can not only calculate it due to the ground state. In this case, the excited state also participate for the calculation of magnetic moment. Okay, but if you will monitor the magnetic moment at lower temperature for europium, you will come to know that the value is 0. Right? Because in that case, there will be no provision of moving the electron from ground state to excited state. Or you can say that the excited state do not participate in the calculation of magnetic moment at lower temperature because there will be no thermal motions. Right? So this is the reason samarium and europium shows the observed value different from the calculated value. Again, I will repeat. In case of samarium plus 3 and europium plus 3, the spin coupling is only about 300 to 400 centimeter inverse. This means that the energy between the ground state and next higher state is quite smaller. Right? And the energy which is related between the ground state and next excited state can be achieved by the thermal motion. Right? And due to this, it can not only be calculated by the ground state. These excited states have higher J value and they do contribute for the calculation of magnetic moment. However, if you find out the magnetic moment at a lower temperature, it gives a value near to 0, which we have get it in case of calculated. Right? So this is the reason they do differ at room temperature, or they do differ with respect to the calculated and observed value in case of magnetic moment, especially in samarium plus 3 and europium plus 3. Okay, now let us move ahead. One question I will ask, it's a homework. Cerium plus 4 and yttrium plus 2, what will be their nature? Cerium plus 4 and yttrium 2 plus, what will be their nature? Now see, this is the graphical depiction of magnetic property. See this dotted line, if you are seeing, this dotted line used to belong the spin contribution, and the solid line belongs to the experimental, are basically achieved by the spin as well as orbiter. Now see, if you will see this dotted line, right? So what you will come to know that the magnetic moment is increasing linearly, and then it will start decreasing. Why? Because number of untitled electron is going to decrease. Right? Actually, there are the two ways to explain this graph. One is the gadolinium. If you will see this one, gadolinium. You see this one, this element, right? If you will see the dotted as well as solid line, they do collide at the same point, and it belongs to gadolinium. And in the previous slide only, I told you that gadolinium plus 3 is the only element among the 14 element of lanthanide series. In that case, only spin contributions takes place, no orbital contribution. You see that if this solid line, you notice in case of solid line, you see how this type of curve used to be obtained, right? Two hump, right? Whereas in case of spin, the broken line, if you will see, only one highest point used to be obtained, this one, and it belongs to gadolinium. And surprisingly, the dotted line and the solid line get matched at gadolinium. Are both observations reflect to the same story, and that's why I told in case of gadolinium, no orbital contribution takes place. For remaining, if you will see, there is a deviations. If you see for the cerium, the value for the spin is coming in this range, whereas experimentally it is found a bit higher, right? Then you notice for neodymium, then samarium के केस में देखिए, it deviated a lot with respect to spin only, right? So these observations come across from the fact that in case of lanthanide, basically along with spin, another factor is also responsible, and that is orbital contributions. Okay. Now, these four elements, lanthanum plus 3, lutetium plus 3, plus 4, and yttrium 2 plus, these are diamagnetic, right? Why? Because if you will remember the electronic configuration of cerium plus 4 and yttrium 2 plus, right? They do show 4f0 and 4f14 electronic configuration. So basically, all the electrons which are available are paired in nature. That's why they are diamagnetic. Okay. Next. In the previous slide, I showed the unusual shape of spin plus orbital motion curve arises because in case of less than half field, the total angular momentum J is equal to L minus S. Whereas in case of more than half field, if the number of electrons in F orbitals are more than 7, then in that case the contribution is L plus S. Whereas if the electrons are less than 7, then in that case the contribution will be L minus S. You see here. First thing is clear that in case of lanthanide, basically spin as well as orbital both do contribute. If their contributions are uniform, then in that case, this graph should be linearly increased. Agreed? But what you are noticing that it's increase, then decrease, then again it will increase, and then again it will start fall. Right? And here, if you will see, holmium, especially in case of holmium, the magnetic moment is too high. Right? So the reason behind it is that in case of holmium, basically the value of J used to be defined with L plus S, because in that case, in F orbital, more than 7 electrons are available. Right? Now, this is the formula which we used to implement for the calculation of magnetic moment of lanthanoid. One I have shown in the previous slide, where you have written that mu is equal to root of 4ss plus 1 plus LL plus 1. Right? But L plus S, if you will reshuffle those calculations, then you will come to know that basically mu is equal to Z root of JJ plus 1, where G is the Linde factor and J is the total angular momentum. And remember, this J value depends upon two ways. One, if less than half field configuration, then L minus S, and if it is more than half field, then it will be L plus. What is the value of G? It is 3 by 2 SS plus 1 minus LL plus 1 upon 2 JJ plus 1. Okay. So you see how much complicated the G is. First of all, the name of G is Linde's factor, and the value of the G value is plus 1 divided by 2J plus 1. Okay. Now, why? Let us come to the point that why the gadolinium plus 3 shows a magnetic moment where only spin contributions takes part. Let us recall the electronic configuration first. So what you will notice that in case of gadolinium plus 3, F7 will be there, means completely half filled. So now see, if you will write down F7, in what way you can write it? See that. This way you can write it, right? It is root of Nn plus 2. First we will apply root. If spin contribution is there, then in that case formula will be root of Nn plus 2. And what is N? N is the total number of unpaired electrons available in a given element. So in case of gadolinium, if you will see, the total number of electrons available is 7. So we have put it the value 7 here. And if you will solve this, the value will be root 63. So in case of root 63, if you will solve, the magnetic moment will come 7.9 Bohr magneton. Okay, what it will come? It will come 7.9 Bohr magneton. Right? And if you will compare with the table, it also shows that it is belonging to 7.9 Bohr magneton. So what we can do, that our prediction was appropriate, that in case of gadolinium only spin contributions take place, orbital contribution does not play a role. Now again the question is remaining in practice, that in what way orbital contribution does not take part. See, here I have mentioned two things: J is equal to L minus S and J is equal to L plus S. Right? And if you are able to get it the J value, you can put it in this formula and then you will come across with the mu or magnetic moment. Now, in case of gadolinium, if you will see, the total L value if you will contribute. So basically, in case of F, total 7 subcells are there, and every subcell is filled with electrons. In gadolinium, total number of subcells are 7. F orbital. Agreed? Now, in every subcell used to have electron, and if you will put the azimuthal quantum number of every orbital, right? Say that whichever orbital used to have electron, you just add up the azimuthal quantum number. But well, you get p multiplied by 1 plus 2 multiplied by 1 plus 1 multiplied by 1 plus 0 minus 3 multiplied by 1 minus 2 multiplied by 1 minus 1 multiplied by 1. So in short, 6 plus 0 minus 6. So cancel out, will be 0. So basically L is 0. F के केस में 7 की वैल्यू आप लिख लीजिए प्लस 3 प्लस 2 प्लस 1 0 minus 1 minus 2 minus 3. अभी देखिए हर ऑर्बिटल में एक इलेक्ट्रॉन है क्योंकि F7 है. So every F orbital used to contain 1 electron. अभी मैं आपसे बोलूं आप इनका टोटल कैलकुलेट कीजिए. आपको कैलकुलेट करते समय क्या रखना है कि एक इलेक्ट्रॉन है और उसका जो भी वैल्यू है उससे मल्टीप्लाई करना है जस्ट. हाँ, तो देखिए प्लस 3 के केस में क्या होगा, प्लस 3 मल्टीप्लाइड बाई 1 प्लस 2 मल्टीप्लाइड बाई 1 प्लस 1 मल्टीप्लाइड बाई 1, 0 का तो कोई बात ही नहीं. देन माइनस 1 मल्टीप्लाइड बाई 1 माइनस 2 मल्टीप्लाइड बाई 1 एंड माइनस 3 मल्टीप्लाइड बाई 1. So if you will solve this equation, you will come to know that the capital L is equal to 0. बराबर है ना, बिकॉज तो हर ऑर्बिटल में इलेक्ट्रॉन है तो उनका आप अगर सम करेंगे तो नलिफाई कर देगा एक दूसरे को, राइट. तो अब देखिए वेदर यू विल अप्लाई L minus S or L plus S, both the way L is basically 0. So where exactly J is going to dependent in, it is going to be dependent on S. And that's what I'm again and again repeating. In case of gadolinium, only spin contribution takes a part. There will be no contribution from the orbital. If I will ask this question, remember what you need to do. You have to think about what is the value of L. So in case of gadolinium, because it will unpaired electron means half-filled configuration. So here the value of L is equal to 0. That's why it does not take a part in magnetic moment of gadolinium. ठीक है?
So 4F14 का फिजिकली आएगा ना?
हाँ, but 4F14 is basically diamagnetic in nature. I told you, yttrium plus 2 मैंने ऊपर लिखा भी था. ये देखिए रेड वाला. Yttrium 2 plus. In that case, the electronic configuration will be 4F14. Now here, it's a full field configuration, and it's having a paired spin. That's why the nature of the complex will be diamagnetic. But gadolinium will show the paramagnetic nature. Agreed? So basically, from the magnetic moment, 2 to 3 questions usually originated. One, what will be the magnetic moment for gadolinium plus 3? So in that case, you should remember that here spin contribution is going to take part and formula is going to be implemented Nn plus 2, root of Nn plus 2. And you know N value is 7 and then you can calculate. Second thing is that in case of lanthanide, the magnetic property used to be explained by the answer will be spin as well as orbital movement. Transition के केस में केवल spin. Third, what is the reason? So in case of F block element, the spin orbital coupling is having a higher value with respect to crystal field splitting. In your language, I must say that in case of lanthanide, the spin and orbital contribution will be more as compared to the environmental effect. And what is environmental effect? Why environmental effect is less? So because in this case, the F orbital is quite shielded. It is overlying with 5s, 5d and 5s orbital, the remaining orbital. That's why the orbital, the environment, ligand cannot significantly influence the 4f orbital. That's why the ligand field splitting does not take part. Right? It doesn't mean that we can overlook it. We can, for some property, we can basically, but it also takes a part. It is not possible that crystal field splitting can be completely removed. It is there, undoubtedly, but not as significant as it is in transition element. So in case of transition element, basically orbital motion, orbital contribution is pinched, right, by the interaction with the electric field of ligand in its environment. That's why we used to prefer the spin motion only to calculate the magnetic moment in case of transition. ठीक है. Next is that in case of samarium and europium plus 3, why the observed and calculated value do vary? So the answer is that in case of samarium plus 3 and europium plus 3, the spin orbital coupling results 300 to 400 centimeter inverse, and this means that the energy between the ground state and the next higher state is too low. So what would happen that even the electron related to the thermal motion is sufficient to promote the electron from ground state to excited state. So these excited states are basically contribute in case of samarium plus C and europium plus 3 to calculate the magnetic moment, and that's why their experimental value is higher than calculated. Okay, but if you will monitor the magnetic moment at a low temperature, what we will be able to get it? We are able to get it that the calculated and observed value are same, and that is G.
Sir,